Law of conservation of mass has a little bit of summary right down here. It doesn't really matter who it's by for this particular class, but here's what kind of sums it up. The law of conservation of mass states that mass is neither created nor destroyed in an ordinary chemical reaction. We mentioned in the last video the difference between a chemical change and a physical change. In a chemical change, you actually have substances that change chemically. You may start with one substance and end up with another substance. Um, Up above right here is an example of a chemical change. It may take me a second to write some of this down, but you can see at the top we have some kind of solution that is made of calcium and chlorine. So CaCl2, and you added it to this sodium solution here. Na is sodium, by the way. Yeah, we're going to do a lot of work with the periodic table later on in the class where you'll learn a little bit more about these particular elements and the compounds that making them up. But what we have is this solution made of sodium and calcium, and it's going to produce something a little bit different. Notice here it's producing CaSO4. The calcium is no longer with the chlorine. It's with like I think that'd be like a sulfide there. CaSO4. It's going to end up with a sodium chloride solution in a Cl is sodium chloride. That's a salt. And you will find out later, well, I guess you're kind of finding it out now, that what you have on this side of the equation has to equal what's on this side of the equation. So we're going to end up with, you have two Cl's over here, so you'll end up having to have like two of these. Well, but anyway, you'll have more of that overall. But what's going to happen is, notice here the weight is going to be the same on both sides. Even though you are changing things, you are actually changing the substances in here. Even though you're changing those substances, well, you're going to have the same weight. You're not losing mass. Now, even if you have bubbles that were to go up, if you have this stopper here, it would trap those bubbles. So you would not lose weight there. That's kind of what the law of conservation of mass is. When you have a chemical change, the mass stays the same. See what it says here, or more simply, the mass of substances produced, the products, is always equal to the reactants, which is going to be here. And you can see here that we have kind of a little bit of chemical equation here where we have 1 gram of this plus 5.34 grams of this equals, and of course it's going to be the sum of those two parts. So you have 6.34 on either side. Looks like the same thing down here, 12.68 is what this adds up to. So that's the law of conservation of mass. Now, in the last video, we talked a little bit about the chemical change that you get when you're burning a match. Now, let's look a little bit more into that. We had a match which was just wood, and we have oxygen with it because of the oxygen around it. So you have the wood plus the oxygen equals, now what you end up with is going to be ashes. The ashes on the tip, and perhaps some would fall down. And you're going to end up with this gas, carbon dioxide, is part of what's produced, and you have a little bit of water vapor. So that's where the O ends up with coming over here. But what's going to happen is the total mass of the wood and the oxygen is going to equal the total mass of the ashes, carbon dioxide, and water. And what it looks like you start out with one nice piece of wood with the red tip and end up with something different, a little scrawny piece of wood that's burnt. But you also have this stuff which goes out into the air, the water vapor and the carbon dioxide, which equals that same amount. So mass is not created or destroyed. Mass just shifts forms. And that's going to sound similar to this law of conservation of energy. These are the two laws that we're talking about in this video. And you know it's going to be similar. Energy cannot be created nor destroyed. Now that's what we said with mass. So mass cannot be created or destroyed in a chemical reaction. And in any action, energy is not going to be created and it's not going to be destroyed. It is only converted from one form of energy to another. Now we're going to talk about this in the form of potential energy and kinetic energy a lot, and I think it's chapter 9 is what it's going to be in your book. This is kind of the nutshell version before we really get there. Here we have these runners on this starting line. Right now it looks like they are going at zero energy. I mean, they are just still there. And suddenly, whenever the gun goes off, you have all this energy, all these people are creating this energy. So it appears that energy is being created, but it's just that it's being converted. Where do they get the energy to run? They have their muscles, and they have the food that they ate. You can literally dissect and take the energy that this dude right here is using to run and trace it back to some kind of food that he ate, which is giving him that energy. So once they complete this race, then they will have burned off some of the food using the muscles in their body. So you had an equal amount of energy here just as you did here. It's just that here you're burning some of that food off using your muscles. So it looks like there's not that energy is just being made, but it's not. Now you'll find out later that them just sitting at this starting line, or I guess crouching at this starting line, is going to be a form of potential energy. All that food, all the muscles, and so on is a form of potential energy, and you'll find out the actual doing will be kinetic energy later on. Let's see what else we have. Let's take a look at this person with the arrow. This arrow, right now the arrow is still. So it looks like the arrow is not doing any actual moving right now. But when this guy lets go of the string, it's going to go a long way and create energy. There's energy that is expanded whenever this is moving. And you can see what the forces are that are going backwards to create this energy. You have the force that is being pulled back on the string, the tension that is in the bow here because of the string being tightened. It's not a very good arrow there. But the sum of this energy on the string, on the bow, and of this person pulling back is going to be equal to how far it ends up going. Now, if you don't pull it back as far and you don't have as much tension, the arrow will not go as far. I mean, that just kind of stands to reason that the amount of energy that you use in stretching this is going to be equal the amount of energy that is eventually used. Now your book is going to have the example of someone cranking up a car. They're going to say it doesn't appear to have the same amount of energy. I mean, here all you do is turn your hand this way and it cranks the vehicle, and the vehicle has so much more energy, it appears, than what you did to put in it. But the book is going to point out, as it should, that you have a lot more factors into play. You have the gasoline that is in this automobile, this fine-looking automobile with the Alabama sticker on it, by the way. You have the gasoline that is in this automobile, which is a form of potential energy sitting there waiting to be used. You have the pistons that move up and down that are sitting there waiting to be used. So you do have this energy in this car before it actually goes, that all it is doing is just waiting for it to be transformed into what's called kinetic energy. Don't forget to go back and answer the questions. Hope you learned a little bit about energy and mass conservation.